at this Helmholtz event and at KIT. So I'll be talking about particle physics. Particle physics, essentially, what is it? It's the study of the fundamental constituents of matter and their interactions. So you might, all of you are familiar with the atom. You know that there's a nucleus inside. Maybe you know less about what might be inside these protons and neutrons in the nucleus. So we now know that there are quarks and gluons, and we think, until proven otherwise, that these are fundamental particles. A fundamental particle is something that you cannot break into pieces, that you cannot excite. It's basically a mathematical point. So these are, of course, questions that people have been asking since a long time, the ancient Greeks or Goethe in Faust. The privilege that we have today is that we have great instruments to answer these kind of questions. So at the LHC, at the European Laboratory for Particle Physics in Geneva, we collide protons head-on. So shown on the left is what we see in one of these detectors, Atlas, what happens after a collision. So the beam axis, the protons would be going inside into the screen, and then we see an orthogonal view of the debris that comes out of the collision. So we can then identify special particles in this debris, particles called electrons, muons, and we can interpret, try to figure out what happened in this collision. So let's see if we select collisions where we see 2 muons and 2 electrons or other combinations of 4 leptons, we can then count them, right? And we don't just count them, we count them in intervals of mass. That's shown on the right. So for example, at a mass of around 110 units, yeah, in our data set, we found like 5 events. And you do this in different bins or intervals of mass, and then you see this distribution. And what strikes you, well, there are multiple processes that can produce this kind of events, but there is one that seems to be particularly likely at 125 GeV. And that's basically the discovery of the Higgs boson. Nature likes 125 GeV because that's where you have a resonance, a particle which gets produced and then decays and gives this debris that we are seeing here. Okay, so that was the discovery of the Higgs boson in 2012. It's sort of an old story. What have we been doing since then, and what's the next thing? So remember, this is quantum mechanics, where we describe particles using fields. You know the electric field. There are more fields than this. For example, this field denoted phi here on the left. And the Higgs boson is essentially an excitation, a quantum excitation of that field. What is very special, according to theory, about this particular field is that it interacts with a potential that is denoted Vf on this plot. And the potential has such a shape today at the bottom such that the ground state, the most likely value for that field is not 0, but something non-zero. That would be very different from the electric field. What gets even more excited is allegedly, according to theory, the shape of this potential changed a lot since the Big Bang, hot universe, very dense in terms of energy. It then moved to the shape that we see today, and it went through a phase transition where something extremely violent, apparently, allegedly happened right after the Big Bang, and that has huge implications on the universe as we see it today. So according to theory, we had these bubbles that formed in space where the phase transition happens. The bubbles get larger, they collide, they emit gravitational waves that maybe we will be able to see someday. It's interesting stuff. The problem is, to learn more about this potential, we need to study very rare processes of the Higgs boson, right? So it's enough to produce a few tens of them to convince yourself that the Higgs boson exists. But now we want to look for interactions that only 1 out of 1,000 or 1 out of 10,000 Higgs bosons will do. So we need way more data. The problem is we already have a lot of data, and it's actually pretty hard to handle. You can think of it as taking data already now at the LHC is like drinking water out of a fire hose. I've shown you this one event, but we have 40 million out of those per second, and we're running 24/7. So that would be 60 terabytes per second all day long. Of course, there's no way you can record this. Typically, what we record is 1,000 events per second, and that would be 1.5 gigabytes per second. And what we publish is, I've shown you this plot, what's in there, that's just 1,000 events collected over the time span of 4 years. So basically, an analogy would be, you have the rainfall is coming at you, that would be what the detector produces. What we can record is the fire hose, and what we publish is basically these few drips that come out of here. So what we want to do now is, in our field, we are used to using AI for analysis, for example, event classification. Is this signal blue or is this background red? We've been doing this for a long time, but the thing that we are attempting to do now is use AI to deal with the data that comes out of the fire hose. We want to use AI and run it on every single event that we record. And I will explain to you in a second why that is so important. Just one more thing. Where do we run all this computing? So we basically just to the centralized pre-processing of all of these events is done worldwide in 14 computing centers. The one that I know best is the one in France at the bottom. And some of you may have visited Gridka at KIT on Monday. That is another one of these 14 sites. What will happen now in order to get more access to rare events is that we need to increase the collision rate. I didn't tell you these protons don't come as a continuous beam, they come in bunches. And we cannot put in more bunches, the only thing we can do is put more protons into each bunch. So what will happen is we will have a lot of stuff in the detector, and our problem is we need to get back. We don't see these tracks of particles, we see hits left in individual layers, and we need to find all these 10,000s of particles that left these hits. So we knew that this is coming at us. Standard methods that we've been using so far will not get this done. We need to do business differently, and that's where the idea of coming, why not use AI for pattern recognition? So we have these hits that come from the detector. We represent them as a graph where the nodes are hits and the edges are possible, and an edge means this is a possible step from one hit after the other of a particle that went through. And then you can formulate this problem as an edge classification problem. And so the idea, to give you an idea of the time scale, the idea of doing this, representing our data as a graph, dates back to 2017. A proof of concept, we have published it in 2021, and we are now at the stage where we are trying to figure out how to actually run this at scale. And I think I've tried to explain a little bit what the scale is. So we have the fire hose that delivers the data, and we need to run this seamlessly on a GPU. The idea is to ship the hits to the GPU, everything happens there, and you get back particles and estimates of their parameters. So for each one of these steps, we pick the best solution. For example, GNN inference, that's something pretty standard, right? People do this in the industry. We are using the usual products, PyTorch and so on and so forth. The first time I did this, I was a little bit like this guy on the left. I was wondering, what is the inference time per event on a given piece of hardware? And I was a bit surprised when we got all these different answers. One LibTorch version does this, the next one gives you this. So it's actually a pretty active field of development. For me as a particle physicist who has done 25 years of computing on CPUs where we understand everything very well with benchmarks, that was a bit of a new situation. And of course, the other thing that is new is not everything is done by industry or by others for you. GNN inference is, but data preparation is not, right? So how do we efficiently transform our hits into graphs? That is something where we wrote our own piece of software, which is publicly available. We call it Module Map Graph. Anyway, it doesn't matter. But the idea is, it was very tough actually for us to have people learn CUDA and think the way you need to do in order to run on these massively parallel hardware and come up with algorithms that do this. And we are now actually pretty happy with this. It really uses these GPU resources very efficiently. So we are getting to the point where we are able to actually take data from the fire hose, run it consistently through the GPU, and we are now trying to deploy this at scale. For this high luminosity run that will start in 2030. So the three of us, Sylvain and Catherine, all of us will be at the poster session as well. So don't hesitate to drop by and discuss with you. We are really interested in seeing experience that other people might have with this kind of problem difficulty. Thank you.
Thank you. Any questions from the audience?
Okay, thank you for the very nice talk. So if I understood correctly, the issue is you have a too high flow of information for you to record everything, so you want to somehow condense this information using neural network processing. So are you not afraid of losing actually most of the useful information in the process?
That is a worry, but we've been living with this since always, right? This is the situation as it is already now. We have this, we call this the trigger, the event selection, and most of it is discarded forever. So it's, some people also try to maybe put have AI look at the events that we discard, but that's a separate topic. But for us, the situation is fundamentally not new, and we are always worried about it, and yeah.
So I guess what the neural network would do would look like a selection of what's interesting actually in what you record.
Yeah. So I mean, in the first step, the decision to record an event, yes or no, the deliverable is a yes or no decision, right? What I presented here, we use it for offline reconstruction. So it's actually the precise assessment of all of these particles in our events that go into the final plot.
Okay. Thank you very much.
So that almost answered my question. I'm a colleague from CMS. So I was wondering whether you thought about implementing this like in the high-level trigger instead of offline.
Yeah, so it's basically the same algorithm that is a candidate for the high-level trigger and for offline. I am personally working on offline, but it's the same thing online. Remember Atlas, we had this idea to use custom hardware that was trashed some years ago, and we might be using GPUs instead at the high-level trigger.
Just hi, this is Peter. Just a nitpicking or hair-splitting question. So the track reconstruction algorithms have been ingrained with generations of knowledge mathematically. You benchmark against those. How does your algorithm deal with the problem? So my question is, in these pileup events, you have a lot of ambiguity because the tracks are super close or even overlapping. Does the GNN actually pick that up? So how does it compare to the mathematically biased algorithm?
So the classical algorithm would be, for example, a Kalman filter. So our field has been doing this since the 1960s, and it is true there's a lot of experience there. So what we did is we start by doing efficiency plots, right? You simulate what is the efficiency, and the GNN is slightly better than the Kalman filter. And we push this even to track-by-track comparisons, right? We say, what is the kind of mistake that the GNN made, and most of them are, you know, delta rays are a hassle, right? The Kalman filter gets fooled, we get fooled.
Okay, thanks.
All right, let's thank the speaker again.